Hey, AP Chemistry, I'm coming to you again with some solutions to some of the FRQs from that practice test that I gave last week. This is from the 2014 practice test. There it is. And you guys had questions about number 3, number 5, and number 7. It was very nice, the odd numbers. And I want to go over them. So the first question is about this setup here, a galvanic cell, where we have a tin electrode submerged in some tin nitrate and a copper electrode submerged in 1 molar copper nitrate solution. They have a salt bridge between them. It's potassium nitrate, and then there's a voltmeter over here, and the presence of the switch doesn't really matter, but that's the setup here. It says a student is given, raise that up there. A student is given a standard galvanic cell represented above that has a copper electrode and a tin electrode. As current flows to the cell, the student determines that the copper electrode increases in mass and the tin electrode decreases in mass. And the first question is identify the electrode at which oxidation is occurring. Explain your reasoning based on the student's observations. So the first thing when you read this is probably to draw on the diagram or make your own diagram like I did quickly. The thing that they tell you is that the tin electrode is losing mass. Remember that when oxidation is occurring at the anode, the electrode solid, the solid electrode, the metal that is there, is going to be oxidized into the ionic version of that metal, and it's going to go into the solution. So this tin, I'll draw it, this tin is being oxidized to tin 2+. And they say that the reason I know that is because it's losing mass. They say the tin electrode is losing mass and the copper electrode is gaining in mass. So I know that the tin metal is basically being eaten away. It's being oxidized, it's rusting essentially, and that metal is going into the solution of tin nitrate as tin 2+ ions. They also tell us that the copper electrode is increasing in mass. So that means that the reduction is occurring at the copper electrode because the copper 2+ ions that are in the copper nitrate solution are being reduced. They're gaining electrons to become copper solid, plating onto that copper electrode. So oxidation is taking place at the tin electrode, that is the anode. The anode is the location of oxidation. Next question. As the mass of the tin electrode decreases, where does that mass go? And I just kind of answered that. We can say that the mass is going to the solution as tin 2+ ions. Why is that happening? Remember, tin is being oxidized, so the tin metal is losing its mass, and that mass is being transferred, so to speak, into the solution. So the electrode is losing mass and it's being gained by the solution. And so that's where the mass is going. Part C, in the expanded view of the center portion of the salt bridge, shown in the diagram below, draw and label a particle view of what occurs in the salt bridge as the cell begins to operate. Omit solvent molecules and use arrows to show the movement of particles. This one's not too bad. Remember that the salt bridge is used to balance the electrical charge in both half cells of the galvanic cell overall. So at the tin electrode, we know what's happening there. The tin is being oxidized to tin 2+. So you can think of it as the anode solution gaining positive charge. And then on the cathode side, where reduction is occurring, the copper 2+ ions are being reduced to copper solid and plating onto that copper electrode. So on this side, on the reducing side, we are losing positive charge. So there's an overall negative charge that's forming on the cathode side. And on the anode side, we're gaining more tin 2+ ions in that solution. So this side is gaining an overall positive charge. Now, in order for the cell to continue operating, you must have balanced charges in both solutions. So the salt bridge is used to make sure that ions are drawn to one side or the other so that you can have that balance of charge. And so what's going to happen? Since the tin 2 plus is accumulating over here, you're getting an extra positive charge. The salt bridge is going to dissolve, and nitrate ions are going to go towards the anode to balance out the extra tin 2 plus charged ions. And then the potassium ions are going to move towards the copper side, the cathode side, where we're losing positive charge, therefore getting more negative. And so the potassium is going to balance that charge over there. And so that's what's going on. Remember, the salt bridge is used to balance the charges overall. Okay. The next few questions have to do essentially with the Nernst equation. That's D. A non-standard cell is made by replacing the 1 molar solutions of copper nitrate and tin nitrate in the standard cell with 0.5 molar solutions of copper nitrate and tin nitrate. The volumes of solutions in the non-standard cell are identical to those in the standard cell. Part I, is the cell potential of the non-standard cell greater than, less than, or equal to the cell potential of the standard cell? Explain, justify your answer. So the answer to this question can be figured out by remembering the Nernst equation. The Nernst equation is used to determine the cell potential of a galvanic cell if the cell now no longer has standard conditions. And one of the standard conditions is where the solutions are 1 molar. Now they're 0.5 molar. Now remember what the Nernst equation looks like. It looks like this. So the cell potential, the non-standard cell potential, is equal to the standard cell potential minus 0.0591 over n being the number of moles of electrons transferred in the process, times the log, and this would be Q, the reaction quotient. And the product of this reaction is the tin 2 plus ion that's being oxidized from the tin metal. And then the reactant, the copper 2 plus, is being reduced to copper solid. We take out the solids from the reaction quotient because solids are not put in the reaction quotient. Now, with this situation, we have 0.5 molar solutions. What's the net effect? We haven't changed anything at all. There's no change because the 1 molar, it's still 0.5 over 0.5. So Q has no effect on the overall cell potential. So the standard cell potential is going to be the same as the original. Or the new cell potential, let me say it again. The new cell potential is going to be equal to the standard cell potential. We have 1 over here. The log of 1 is 0. So this whole part of the equation goes away. And therefore, these two things are equal to each other. Now the next question is part I. Both the standard and non-standard cells can be used to power an electrical device. Would the non-standard cell power the device for the same time, a longer time, or a shorter time as compared with the standard cell? Justify your answer. This just really comes down to the fact that in our cell, we have a 0.5 molar solution with the same volume. So overall, we have fewer moles of copper 2 plus that are available to plate onto the copper solid. In the same way, well, I guess the tin doesn't really matter. We're going to run out of copper 2 plus. We're going to run out of copper 2 plus on the cathode side because there's now only 0.5 moles of it as opposed to 1 mole of it like last time. So in this case, fewer moles of copper 2 plus, that will cause the reaction to stop sooner. So the device will be powered for a lesser amount of time in this case. Okay. Next question. In another experiment, the student places a new tin electrode into a fresh solution of 1 molar copper nitrate. So we've got something kind of like this. We've got just a tin electrode placed into copper nitrate, and you're going to have still a galvanic cell kind of reaction. Redox reaction is going to occur. And they ask us, after giving us these values here, using the information from the table above, write a net ionic equation for the reaction between the tin electrode and the copper nitrate solution that would be thermodynamically favorable. Justify the reaction is thermodynamically favorable. So in order to answer this question, you got to remember what's thermodynamically favorable when we talk about voltages. Remember that voltages that are positive have a negative Gibbs free energy. So we want to set up an oxidation reduction half reaction addition so that we have a net positive voltage. Couple tricks in this one. Okay, you got copper 2 plus in this solution. Okay, that means that your copper, you're looking for your copper 2+ in the table here. So we're going to use copper 2+, not copper 1+, because this solution has copper 2+. So copper 1+ is not going to be utilized for figuring out what is the half reactions. And then you have tin 4+ and tin 2+. We need to figure out which of these reactions is going to be utilized in order to get a positive cell potential. Now, thinking about this logically, look at my diagram here. Tin is going to have to be oxidized, and copper is going to have to be reduced. So copper is actually going to plate onto the tin in this case. So we need to use either the tin being oxidized, or we need to figure out which of these is going to give us a positive oxidation potential. Remember, these are reduction potentials. So I'm going to use the value that's negative, because remember, this is reduction. So when I switch it to oxidation, the tin being oxidized, I want to have a positive cell potential there. So I'm going to use this value right here. I'm going to use the tin 2+, because when I flip the sign here, it's going to be positive. It's going to be positive 0.14. And then copper 2+ over here, this is being reduced. The copper is going to be reduced, and it's got to be copper 2+ because I've got copper 2+ in this solution. So it's going to be 0.34 plus 0.14. This is I'm going to flip this one because this is the reduction reaction equation, but I'm going to be oxidizing the tin. So I'm going to flip it. And then this is the reduction. Copper is being reduced. In this case, copper 2+ is being reduced. So I use this value. I use copper 2+ because copper nitrate, copper 2 nitrate is copper 2+. All right, so kind of wrote that all over here. And then I added the values together. So the tin oxidation and the copper reduction added together give us 0.48 volts. And then the next question was calculate the value of delta G for the reaction. Now this question, I'm 99.9% would not be on the test this year because this is technically part of Unit 9, which is the applications of thermodynamics. Regardless, we might as well answer it just in case something like this were to come up. So, kind of running out of room here. Remember this equation, it's given to you on the reference sheet, would find the Gibbs free energy of this reaction based off of the cell potential. So the number of moles of electrons that are transferred is 2. Why is it 2? Because we've got this going on here. Oops, can't see that. So the copper 2+ is being plated as copper solid. We've got a transfer of 2 electrons here. So 2 moles of electrons times Faraday's constant times the cell potential 0.48 volts gives us this value right here, negative 93,000 joules per mole, or negative 93 kilojoules per mole. That's the Gibbs free energy. That one's not too bad. That's just a basic calculation. Okay, and that's just kind of using the equation. Number 5, this one's a fun one. So we're given some compounds and metal or nonmetals that bind with fluorine. And it says some binary compounds that form between fluorine and various nonmetals are listed in the table above. A student examines the data in the table and poses the following hypothesis. The number of fluorine atoms that will bond to a nonmetal is always equal to 8 minus the number of valence electrons in the nonmetal atom. A, based on the student's hypothesis, what should be the formula of the compound that forms between chlorine and fluorine? Okay, so that he's saying, or she, let's not give a gender, I guess. This student says that it's 8 minus the number of valence electrons on the non-metal that binds with the fluorine. Okay. So what should the formula of the compound that forms between chlorine and fluorine? So let me just read it again. The following hypothesis, the number of F atoms that will bond to a nonmetal. So we're talking about fluorine binding to a nonmetal. In this case, it's chlorine. So it's going to be 8 minus the number of valence electrons in the nonmetal. In this case, the nonmetal is chlorine binding to fluorine. And what is it going to be? So chlorine has 7 valence electrons. It's halogen. All halogens have 7 valence electrons. So 8 minus 7 equals 1. So 1 fluorine should bind to the chlorine. So ClF would be the equation or the formula of the compound based on this hypothesis. B, In an attempt to verify the hypothesis, the student researches the fluoride compounds of the other halogens and finds the formula ClF3, chlorine trifluoride. In the box below, draw a complete Lewis electron dot diagram for a molecule of chlorine trifluoride. Well, chlorine's going to have to be in the center. You always want to try starting off by making a skeleton. Chlorine in the center, and then the fluorine's off kind of in a triangle. And then you want to figure out how many electrons are going to be in that electron dot diagram. And so we've got 4 atoms. Each of them has 7 valence electrons. So we're going to have a total of 28 electrons. And the thing to remember here is that you need to have 8 electrons around everything to fulfill the octet rule. So we're going to draw 8 electrons around fluorine for each of them, and a single bond to each of them from the chlorine. Then you still have 4 electrons to take care of. Remember that chlorine can expand its octet, so we would actually add the 2 extra pairs of electrons onto chlorine because chlorine can expand its octet. So this would be the diagram that would be correct. Next question. 2 possible geometric shapes for the chlorine or ClF3. Can I have a drawing somewhere? Oh, there it is. Okay. 2 possible geometric shapes for the ClF3 molecule are trigonal, planar, and T-shaped. The student does some research and learns that the molecule has a dipole moment. Which of the 2 shapes is consistent with the fact that the ClF3 molecule has a dipole moment? Justify your answer in terms of bond polarity and molecular structure. So basically it's saying ClF3 is either going to be T-shaped or it's going to be trigonal planar. So it's either going to be, I'll draw it again down here. So the answer is T-shaped. It's either going to be like this or it's going to be this would be trigonal planar. So this would be T-shaped, has a T shape to it. And they say the compound is polar. It has a dipole moment. If trigonal planar were the right answer, that doesn't make sense. They said that. It can't be trigonal planar because there's no dipole here. We've got a chlorine-fluorine bond, and fluorine, though it is more electronegative, there's no dipole everywhere here. It's electronegativity is pushing out in every direction around the chlorine to the fluorine. But with T-shaped, well, you've got these 2 which essentially cancel each other out, but you do have this fluorine down here, which would give it an overall dipole. So yes, it has to be T-shaped because the compound is, we're told it's polar, so therefore it has to be T-shaped. It can't be this because trigonal planar with all the same element around the chlorine would not allow for a dipole moment. 5D. In an attempt to resolve the existence of the ClF3 molecule with the hypothesis stated above, the student researches the compounds that form between halogens and fluorine and assembles the following list. Based on the concepts of atomic structure and periodicity, proposing modification to the student's previous hypothesis to account for the compounds that form between halogens and fluorine. All right, so we're really just worried about Cl, Br, and I, not F, because it's just F2. Basically, he or she, again, I did that, wants to know, well, what's the logic behind what we figured out here? So the student has figured out that we've got ClF and ClF3. They've also figured out that you have BRF, BRF3, BRF5, and then IF, IF3, IF5, and IF7. So there seems to be some kind of pattern here. There's an increasing number of molecules that the fluorine can make with another halogen. And it also seems like every time you go down the periodic table in the halogen group, you get another possible molecule, and it's always going to have more of the fluorines bound to that central atom. They want to know, well, what's the logic? How can we change the hypothesis? So when you respond to this question, it's basically just writing a statement. And they just wanted you to say that, well, based on the evidence, you have a few things that the student can say. Number 1, the number of atoms of fluorine on that central atom is always odd. You have 1, 3, 1, 3, 5, 1, 3, 5, 7. So fluorines are always going to be oddly numbered bound to the other halogen. And then also 2, as the atomic number of the halogen goes up, so as we go from chlorine from bromine to iodine, the number of fluorine atoms also increases. And so that's really it. So it's always odd, and then you always get more fluorines that can possibly bind to that central halogen as you go down the periodic table. And that's really all you have to do with that. Okay, and that was number 5. And number 7. We're looking at this reaction right here. This is an isomerization. For those of you going into organic chemistry in the future, isomerization just means you're shifting the position of one of the groups in the organic compound. In this case, you have cis-2-butene. So why is it cis? Well, it's cis. Cis means on the same side. And so the methyl groups here on the same side of the carbon. Trans here means they're on the opposite side of the carbon. So this actually has an effect on reactivity and things like that. But cis, we're doing isomerization, going from a cis-butene to trans-butene. And we're given a lot of information here. Number 7, the half-life of the catalyzed isomerization of cis-2-butene gas to produce trans-2-butene gas, represented above, was measured under various conditions as shown in the table below. And so we've got trial numbers 1 through 4. We've got the initial partial pressure of butene, the volume, the temperature, and the half-life. The half-life has actually been measured. And they say this: the reaction is first order. Explain how the data in the table are consistent with a first order reaction. Now, when I first looked at this, I said, that's interesting. We've got trials 1 through 3 here. And the big thing is, in trials 1 through 3, the temperature's the same, but we change in number 4. So I'm actually going to throw out number 4 because when we change the temperature, we're going to change the kinetic energies, and we're going to change activation energies and stuff like that. So that one really is not going to be used. But 1 through 3, we have the same exact half-life. And the thing to remember is this. So first order reactions, if we're being told it's first order, have half-lives that are independent of the partial pressure. So you'll notice here that we have 300, 600, and 300, but we changed the volume a couple times. We still have the same half-life though. So first order reactions have half-lives independent of the partial pressure or concentration. So concentration, or in this case, partial pressure. I wanted to write these out here. So a zero order half-life is equal to this. It's equal to the initial concentration over 2 times the rate constant. For a second order reaction, the half-life is equal to 1 over K times the rate, or the concentration, times the rate constant. But one doesn't have the initial concentration here. So first order reactions do not involve, they're not dependent upon the initial concentration. And that's what we're seeing here. It doesn't matter what our concentration is, we still have the same half-life. And so something to keep in mind is that first order reactions have half-lives independent of their initial concentration. So the half-life is equal to the natural log over K. So we see that the concentration, or in this case partial pressure, has no effect on the half-life, even though we're changing it in the data. And we still have 100 seconds as the half-life. Part B, calculate the rate constant for the reaction at 350 Kelvin. Include appropriate units with your answer. Okay, so I wrote this wrong. I looked at the second order accidentally first. So the half-life is equal to the natural log over K. We want to solve for K, that's the rate constant. So K is equal to the natural log over the half-life. So it'd be natural log of 2 over 100 seconds. And so you get this, 6.93 times 10 to the negative third. This value would be given to you on the reference sheet, so you don't have to worry about that too much. Question C. Is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Justify your answer. Now, this is kind of a confusing question because it's like, well, how is rate going to be connected to concentration or partial pressure? And it's really easy. It's actually not too bad. It seems so weird. Remember that the rate is the rate law. You can calculate the rate law, or the rate of a reaction, from the rate law. And we know the rate is first order, or the rate law is first order. So rate is equal to K times the partial pressure of the cis-butene. Whatever's bigger here. K is the same for both. Whatever's a bigger value here is going to be a faster rate. So it also means if you start with a lot of stuff and they're all over the place and they're doing things, they're going to bump into each other more because there's more of them. So the rate at which the reaction begins at is going to be larger. If we have a smaller amount of the cis-butene, then there's going to be less reactivity because there's fewer of them, so they're not going to react as much and decompose. So rate in trial 1 is less because we have a smaller partial pressure. There's fewer molecules in that space, and so you're going to have a reaction that is at a slower rate at the beginning. And you can prove that with math using the standard equation, or you can just use it. You can just do the logic of there's fewer molecules to react with one another, so there's going to be a slower rate at the beginning for trial 1. Last question. The half-life of the reaction in trial 4 is less than the half-life in trial 1. Explain why in terms of activation energy. And you can figure this one pretty quickly. Trial 4's temperature is higher, so the half-life is a lot earlier. The reaction is at a higher temperature, so these cis-2 butene molecules are moving around quicker. They have greater kinetic energy, so therefore they are going to isomerize to the trans-butene quicker. So the half-life is going to be less. There's going to be less time necessary to do that. So just want to write something like this. So the temperature increased in trial 4, so more molecules of cis-butene have sufficient energy to isomerize, so the half-life is less. It's a shorter half-life in order to do that. Okay. All right, that's your questions from last week's practice test. Remember, you have one more practice test this week. This one's actually a shorter one overall. Still do a good job. I hope you guys are working on that. If you have any questions, let me know. Post those into the discussion board. I hope you have an excellent day. I'll see you next time.